So having looked at the right hand grip rule, we're now going to take this a little bit further. And what we're going to do is we're going to look at a horizontal plane circular coil with the current going clockwise. This is the example that you have in your pack. It's the second of the 3 examples. And what we're going to do is we're going to examine the right hand grip rule and where this leads when applying this to a circular coil with a current in it. Quite interesting. So let's have a little look at what goes on. I'm going to draw that plain circular coil. There's your current going clockwise. Now what I want you to think of is this in 3D, if you would. Let's imagine that part of the current loop that's at the top part of the page is actually at the back. So it's kind of going into the page. And then you have the part of the current loop here below, which is actually sticking out in front of you. And what we're going to do is we're going to examine the direction of the magnetic field lines at 4 different places around this circular coil using the right hand grip rule. So what I want you to do is try and practice alongside with me. Take your right hand, let's go for position 1 first, and put your thumb in the direction in which the current is going and wrap those fingers around. So hopefully what you can see is your fingers are going to go down into the page and then back up and round. So I shall try and illustrate that like this. So your fingers are going down into the circular coil and then back up and round. So let's move round to position number 2. Now my hand will actually drop off where I'm sitting at the moment if I try and do that, but if you give it a go, and then you will end up with putting your thumb to the right and your fingers again will go down through the middle of the coil with the field lines coming up and behind it. Let's try position 3, that one's easier. So your thumb is going now down the page and your fingers are going to go down through that circular coil and then back up the other side. So we've got field lines going down through the middle, then back up the other side. And then finally, in position 4, you've got your thumb going to the left there, and your fingers again are going to go down through the center of that circular coil. So what we've got is something that's actually quite consistent. You will notice that in all 4 positions, the field lines are going down through the center of that circular coil. Hang on a minute, let's go back to a bar magnet. In a bar magnet, we know that field lines come out of a north pole and into a south pole. Hang on, look. They're all coming out of the bottom of the circular coil and going down into the middle of the circular coil from above. So if you're looking at this circular coil from above, the field lines are all going into it. As you look down then, it therefore becomes the south pole. If you imagine looking up on the underside of that circular coil, then all the field lines are coming out of it. That means the bottom side now becomes a north pole. Oh, that's clever, isn't it? So we can think of this either as a plain circular horizontal coil, or we can think of this as a solenoid, so a continuous loop of circles, if you like, means the solenoid will have a north and a south pole. So if you go back to trial 5 for your 3rd example, you can now hopefully find which is the north pole and which is the south pole of that solenoid. Now, you can use the right hand grip rule for looking at solenoids or horizontal plane circular coils. Or there's a little bit of a tip here that I have for you. So let's have a little look at this. Let's imagine that you're looking down on the circular coil and that you have a current, first of all going in a clockwise direction and then going in an anti-clockwise direction. And you'll notice that I have put the arrows in a very particular place. I've put them at 8 o'clock and I've put them at 2 o'clock. Okay. Now, the reason that I've done that is because the letters N and S fit very snugly inside those arrows as you draw it within the circle. Let me show you. So you can see that the end of the letter is fitting inside the head of each of those arrows. And we can do the same with the North Pole as well. There we go, it's a slightly strange N, but it is an N, recognisable. Again, the ends of the letters fitting the inside of those arrows. So there's a little bit of a trick. So if you see current travelling in a circular pattern, then you can either go down the right-hand grip rule route, or if you're happy doing this and don't want to go through the process of the right-hand grip rule, then you can simply draw your arrows to an 8 o'clock and decide then which letter fits within those arrowheads. Quite handy. So then just remind you on the 3 little tips, tricks, conventions that we've shown you so far. Number 1 was on field lines coming out of a bar magnet or wherever else. They must be, first of all, in a closed loop. They must be such that they never cross, okay? And they always come out of a North Pole and into a South Pole. The second thing I showed you was back to the days of bows and arrows, and it allows us to illustrate things in 3D that are actually in 2D on our page. So you can either have this illustrating a current coming into and out of a page. So remember, that is coming out. That's the tip of your arrowhead, and that is going in, and those are the feathers of your arrow going away. So this could be current coming into or out of a page, or it could be field lines coming into or out of a page, and it's just a way of representing a 2D idea in 3D, okay, or the other way around even, 3D in 2D. Okay, well hopefully that's helped a little bit with your trial 5. Await more videos from now on.